we are going to start talking about a couple different things. We're going to do naming with our polyatomic ions, and we are going to look at some of these compounds that take on multiple charges. Okay, we're going to look at those items on the periodic table that can take on multiple charges. Usually, where are those found? Where did you notice that those are found on the periodic table? Elements that can take on multiple charges. In the transition metals, yeah, right in the middle. Okay, those transition metals sometimes can take on multiple charges. And we have to find a way to differentiate which version, basically, of those elements we're looking at. Okay, if we're working with copper or if we're working with nickel or cobalt, they can take on multiple charges. So we need to find out which of those versions we're talking about. Okay, so get out that periodic table of ions if you don't have that out yet. And let's start looking at some of these items that take on multiple charges. Okay. Let's start with a compound that looks something like this. Let's say that I have, let's say first that I have a compound that looks like this. Okay? Can anyone name this compound for me right off the bat? Copper oxide. That's it. Copper oxide. Okay, because the cation, which is copper, its name doesn't change at all. The anion, which is oxide. Okay, now we have to differentiate. Are we looking at copper with a +1 charge or a copper +2 charge? How can we tell by looking at the compound itself? Yeah, we know we have two options, but this name doesn't tell us anything. Okay, this compound will tell us which version of that copper element we're looking at. Okay, and so we start by looking at the anion that is paired with it. We know that overall the molecule has to be a neutral molecule. So if we know that oxide's charge is -2, and we have one of those, right? We only see one oxygen atom, or oxide. And we only see one copper atom. What does the charge of copper have to be? +2. Okay? So when we write the name of our molecule, it's not just copper oxide, it's copper 2 oxide. Okay? Those Roman numerals that are listed beside that element, that tells us the charge. That's all that there is different about these molecules when we take on multiple charges. The only thing that's different is that we have to add that Roman numeral. Okay? If you give me a transition metal that has two possible charges without the Roman numeral, it is wrong because I don't know what version of that element you're looking at. So if it has multiple charges, you have to include the Roman numeral of the correct charge. Okay, does that make sense? So if I looked at a molecule that looked like this, what would that name be? Yeah, it would still be copper oxide, right? It's still a combination between copper and oxide, but this time we know oxygen has a -2 charge, but we've got 2 of our copper atoms, which means each copper atom must have a charge of what? +1, which means I need to have copper 1 oxide. Okay, the Roman numerals go in parentheses just like that. And that's how you would show that. Okay, so when copper takes on a different charge, it builds completely different molecules. These two compounds, even though they have the same name, behave way differently. They have different physical and chemical characteristics. So we need to understand which version we're working with. Okay, if I gave you a molecule that looked something like this, let's start trying to name that molecule. Okay, give me just the base name here without the Roman numeral. Iron sulfide. Good. Now we go back and we try to determine, okay, which version of iron are we looking at here? Okay. And we can do it a couple different ways. We can reverse our cross method. Okay, it works backwards too, because that would leave us with iron 3 and sulfur 2. What signs do we know have to go with each of these, right? What does this always have to be? Positive, and this one always has to be negative. Okay, so you could do the reverse just like that, and that shows us that we're working with iron 3 sulfide. You can also use your balancing charges method, right? If I know that sulfide is a -2 and there's 3 of them, that means that the anions altogether equal -6. I know that there's 2 of these that has to equal +6, which means my x, or my missing value, is +3. Okay, does that make sense how you can check yourself both ways? Okay, using both methods you can check. Nickel 3 chloride. Okay, so let's try to build that compound. The only thing that's different from what we did yesterday with that is that we know the charge of nickel. That's all the Roman numeral is telling us, is that we know that nickel is a +3. So we're going to start with our molecules individually. Okay, and chloride has a charge of -1. So we can cross these down, or we can look at them in terms of the charges, which would give us NiCl3. Okay, nickel 3 chloride. Let's say that I have manganese 4 iodide. Manganese here is not Mg, it is Mn. Okay, be careful, there's a difference between manganese and magnesium. How many of you wrote Mg right off the bat? Okay, that's good. Okay, it's okay, that's an easy mistake, but manganese we know is plus what? 4. Okay, good, you can read the Roman numerals. +4. Iodide is just an I, and its charge is -1, or negative, or whatever you want to say that. Okay, -1. If I've got a +4 on this side, how many of those iodide molecules do I need to have to balance that out? 4. Okay, so that's where my cross down comes again. Okay, I've got 1 manganese atom, and I've got 4 iodide atoms to balance that out. Okay, when we cross down, remember we drop our charges completely, and we just cross down the number. Okay, we leave the 1 off because whenever there's a 1 subscript, we don't need to include that.
So on manganese, is there only a +2 and +4 charge? There's like no +3?
These on your polyatomic ion, your periodic table of ions, these are the most common charges. So there may be a time you would have manganese 3, and you would just name it just like you're supposed to. So just go with the Roman numeral that you're given, but these are the most common ones. Yeah. Does that make sense? So if there's a Roman numeral listed that's not on your table, that's okay. That's a possibility, but these are just the most common ones that we use. Okay? Okay, thank you. I'll go fix it. Alright, let's try these 4. What happens if we don't have a Roman numeral here? Yeah, it only has one option, so there's no need to include it. Okay, so if you're going the other way, if you were going name to, or so if you're going compound to name, and there's only one option for the charge, don't include the Roman numeral. Okay? Can I have a volunteer for the final answer here in words? Yeah, Dom, go for it.
Gold, 3 phosphide.
You said gold, 3 phosphide. Do we agree? Okay, I would agree there. Phosphide has a -3 charge. We only have, a -3 charge. Gold, we only have 1 atom, so that means gold must have a +3 charge to balance that out. Okay, any questions there? Okay, the second one, silver fluoride. Can I have a volunteer? Jack, go for it. AgF. Very good. Those have a +1 and a -1 charge, an easy combination. Good. Okay. Again, silver did not need a Roman numeral because it only has one possible charge. It's always a +1. Okay. So I did not include that there. I wanted to make sure you could still see it without. Okay. Titanium nitride, titanium 3 nitride. Stone, what'd you have? TiN. Agreed? Good. Okay, so far they've all been pretty easy. And our very last one here, CO2S3. Brett, what'd you have?
I had cobalt, 3 sulfide.
Cobalt. Oops, not just regular 3. Sulfide. Do we agree? Yes, perfect. If we cross those charges back up, we see a +3 here and a -2 with sulfide, which we should agree with. Okay, sulfide normally has a -2 charge. Cobalt, in this case, has to have a +3. Okay, very good. We have polyatomic ions that are both positives and negatives, both cations and anions. Which do we have a majority of? That are anions or that are cations? Anions. We have a majority of anions that are polyatomic ions. Okay, most of them. We have a few exceptions. Ammonium is the exception. I don't know if I gave you another one that was positive or not, but ammonia. Okay, NH4 and NH3 + 1. Okay, so those are our really only 2 positively charged polyatomic ions. The rest of which are negatively charged, which means they're going to act just like the anion in all of our other naming rules, okay? Except they don't end in IDE, okay? The polyatomic ions get to keep their name. So naming with polyatomic ions is extremely easy because the cation gets to keep its name and the polyatomic ion gets to keep its name. So there's really no change. You just have to memorize the polyatomic ions, okay? Does that make sense? So let's try a couple here. Let's say I want to look at a combination between lithium and phosphate. Okay, I wanted to have a combination between lithium and phosphate. Lithium has a charge of +1, good. And phosphate has a charge of PO4 minus 3. Okay? And what that polyatomic ion means is that this whole compound as a whole has a charge of minus 3. Okay, that's what that's telling us as a whole, that whole entire compound. So, when I cross my charges down, or when I start looking at the balancing between these molecules, how many lithium atoms do I need to balance that one phosphate atom? 3. Okay, and if I cross down, it would look like this. Li3PO4. Okay? I only have one single phosphate molecule. Okay, so if I included the 1, it would look like this. It would be parentheses, and I need one single phosphate molecule. But whenever it's a 1, what do? We drop it off. So we don't even need the parentheses in that case. Okay? And let me show you if we have maybe more than one phosphate molecule, what would that look like? Okay? So let's look at a combination between magnesium and phosphate. Okay, if I needed a combination between magnesium and phosphate, magnesium has a +2, and phosphate's charge is -3. So now let's take a look at how we balance these, okay? Let me get rid of lithium up here. Okay, magnesium and phosphate. Mg +2, PO4 -3. Okay, so now let's cross down our charges and then we'll check. Okay, we drop the sign. We cross down our charges, which means we need 3 magnesium atoms and we need 2 phosphate molecules. Can we just go like this? No, because that doesn't tell us anything. We have to have the parentheses so that we know that we need 2 of these entire molecules. Okay, right? We need 2 phosphorus atoms and 8 oxygen atoms. Okay, so whenever we have to cross down with multiple, we need to make sure that we have parentheses around that polyatomic ion. Okay. The name of this molecule. Anyone know? Magnesium phosphate. Okay, because when you have a polyatomic ion there, it just keeps its name. That's why you work to memorize the names. Okay, polyatomic ions keep their name, and the cations keep their name. Okay, so the naming part of this is easy. The combination is where you have to get a little bit more in depth. Okay, the naming part for these polyatomic ions is easy. Questions here? Okay, let's try a couple more. Yeah, sorry, Morgan. Compound. So I have a compound called sodium hydroxide. So let's build that compound. Sodium has a +1. Hydroxide as a whole has a -1. So this combination is really easy, right? It's a 1-to-1 ratio, which means all we do is push them together. NaOH, sodium hydroxide. When there is only one of that polyatomic ion, there's no need for you to put the parentheses. Okay, when there's only one of the polyatomic ion. So if we would cross down our charges, it would look like this. Na1, NaOH1. There's no need to include those ones. Okay, so we leave those off. OH is one of our polyatomic ions, so one of your flashcards. Okay? Let's say I had a compound that looks like this. Okay, you might need your your flashcards out in front of you if you don't know those polyatomic ions yet, okay? So whenever we see a combination like this on the right-hand side, that's a good clue that it's a polyatomic ion. And I just want to know the name of this molecule, the total name of our molecule. Remember, when we named them, the polyatomic ion gets to keep its name, the cation gets to keep its name, so it's simple once you figure out what polyatomic ion it is. Okay. Okay, Kiana, what do you think? Calcium sulfite. Perfect. Calcium sulfite. Lead 3 sulfate. So now we're putting everything we've learned so far into one. Okay, we're combining the Roman numerals aspect and the polyatomic ions aspect. Lead is Pb. Okay, it's a metal. Atomic number 82. Okay, sulfite is SO4 minus 2, right? So after we've got it set up like this, we have to cross our charges down. So lead is plus 3. That 3 is going to come down. The 2 is going to come down, which gives us Pb2, SO4, 3. How many of you got that on your own? Good. Okay, so let's talk through this a little bit more. If we know that lead has a plus 3 charge, and there are 2 of them, that gives us a total of plus 6. Okay. Sulfate we know has a minus 2 charge. There are 3 of them, which gives us a minus 6. Okay, so those 2 combined give us a neutral compound, which is what we are looking for. Okay, so let's try to find the chemical formula of the first and give me the name of the second. Okay, so iron hydroxide, we had 1 iron and 3 hydroxide atoms. To cancel that, for our tin oxide, it has to be tin 4 oxide. Okay?